morning, students. I'm NV Krishna Rao, Assistant Professor, CSE Department. In the previous classes, we have discussed the phases of a compiler design and lexical analyzer and the basics of the finite automata and regular expressions. We continue with the remaining parts. So, we'll continue the discussion of regular expressions and finite automata. A regular definition gives the names to certain regular expressions and use those names in other regular expressions. So here we are giving a regular definition for the some regular expression so that we can use that names in other regular expressions. So the first one is letter, right? A letter will represent small letters A to Z or capital letters A to Z. Digits. Here the word digit is a regular definition which is represent the digits 0 to 9. Here the word sign is a regular definition to represent a sign plus or minus. So regular expression for identify. So what is the identify? Identify is a sequence of the character. The first one is a letter followed by letter or digit. Any number of letter or digit. The first must start with a letter. So we represent this one with our regular definitions. So the first one is a letter. So letter might be capital letter, small letter, A to Z. So we use the word a letter as the first one. Then letter is followed by a letter digit any number of times. So it will be represented by as letter digit. Right? So here this one is a regular expression to represent identifiers in the programming languages. Right? Then regular expression for this one. Right? Here this sign represents 0 or 1. So optional sign followed by one or more digits. Optional sign followed by one or more digits. What is the positive closure will represent? The occurrence of one or more occurrences. So digits. Next comes to the digits. Here digits will be one or more number of digits, numbers. So we will represent digit followed by digit star or simply digit plus, right? So regular expression for the numbers. Number is here a digit followed by optional decimal point followed by numbers. So optional fraction part and optional exponent part. In this expression exponent we may have plus or minus sign. It's optional. E is must representing the exponential. Then 0 or 1 occurrences of sign and optional exponent part. So this is a regular expression to represent numbers. Next comes to the specification of the tokens, recognizing the tokens. What is a token? The lexical analyzer task to read each character by character of input and convert into a sequence of tokens by using the pattern. The patterns are represented by regular expressions. So the patterns are represented by regular expressions. Using the regular expressions, it will generate a sequence of tokens. To recognize tokens, we use the transition diagrams. Right? To recognize the tokens, we use the transition diagram. Now we'll see the transition diagram. What is a transition diagram? Right? So here a regular expression are declarative specifications. Transition diagram is an implementation. Right? So here we represent the regular expression. Right? But to implement, we use a transition diagram. Here, transition diagram consists similar to a flow chart for the lexical lesson, right? It consists the some possible number of states and the transitions between one state to another state, right? So it is to try to represent a patterns to recognize the tokens, right? So for each type of the token, we draw the respective transition diagram. So here, this transition diagram will take the input and move from one state to another state, and if it reaches the final state, then the respective token is generated. Here, otherwise, it will says that it is not the acceptable token. So in these transition diagrams, we use mainly states and transitions. Transitions which move from one state to another state. So now we'll see the recognition of identifiers, keywords and delimiters, relational operators and numbers. Right? We'll see the transition diagram for all these type of tokens. Now, these are words and identifiers. Letters, regular definitions for the letters and digits and sign we already see, right? Letters will represent the small letters and capital letters. Digits represent 0 to 9 and sign will represent plus or minus. So now we'll see the regular expression for identifier. That is, identifier gives letter followed by letter or digit star, right? That is a regular expression. To recognize, we have to draw the transition diagram, right? So here, first initial state 0 will read the letters and goes to the state 1. Here, it may accept any number of letters or digits, right? It will accept any number of letters or digits, right? Here, a regular expression for identifiers. What is identifier? Will result a letter followed by letter digit star. So initially, the initial state 0 will read a letter and goes to a final state. Right? Double circle means a final state. After reaching the final state, it may accept any number of letters or digits. Here, in some programming languages, we use underscore, right? The first character might be letter or underscore. It may be followed by any number of letter or digit or underscore. If we can change this transition diagram respect to that programming language to represent the identifier. Simply a letter or underscore and here letter or digit or underscore. So here we can change this transition diagrams regular expressions which matches to the programming languages to recognize the tokens. So it will return get token insta id. So here how to differentiate identifiers and keywords, right? So here it is a transition diagram to accept the keywords int, if, int, import, float, for. So here we are representing a transition diagram for keywords. Some few keywords. We can have a transition diagram which accepts all the keywords. Okay, at present we are using this transition diagram to represent, to accept the keywords, right? So first it starts with the initial state. Then if I is the input, go to this one state. Then depending on the input, if mn, it may goes to this respective statement, respective transition states. And if it is followed by int t, it goes to int keyword. If it is a if keyword or import keyword, right? It will move one state to another state by reading the character one by one, and it may reaches to the final state. If it reaches the final state here, we say it is a if keyword. If it reaches this final state, we say it is a import keyword. Here, if it is this one, it will be say as int keyword. Then, if it is this one, we say as for keyword. If it is goes to this one, we can say as float keyword. So, F followed by O and R, it's we say as it is a for keyword. If it is F followed by LOAD, we say as it reaches the float keyword. Right? So, this is a transition diagram to accept and to read the keywords if, import, int, for, float. Right? Here, another way is that all the keywords store in the symbol table. Whenever a new token is recognized, then the install ID function will check the lexeme it is already in the symbol table or not. If it is already in the symbol table, then it may verify with the keyword already existing the identifier name. Then, if not matched with any other keyword or existing identifiers, then it will add to the symbol table. Right? So, one way we use the transition diagram for each keyword. Otherwise, store all the keywords in the respective symbol table, so that whenever a new identifier is found, we compare, we check that with the symbol table. If it is already matches with the existing keywords, so we will ignore. Otherwise, simply we save that one in our respective symbol table. Right? The lexeme is installed as an ID token. In either case, a pointer to the entry is returned. The get token examines the lexeme and returns the token name, either ID or name corresponding to the third keyword. Right? One way, writing the flowcharts. Another way, store all the keywords, reserved words in the respective symbol table. So, whenever a new identifier is found, we check it is a existing keyword or not. If not, it is stored in the symbol table. Right? So, next comes to the recognition of the white spaces. Here, what are the white spaces? All the empty spaces, blank spaces, tab, new line are all considered as the delimiters. Right? All the white spaces, tabs, new lines, empty spaces are considered the white spaces. So 0 is our initial state. 0 is our initial state. Then delimiter goes to the a final state 1. And it may recognize one or more number of delimiters. Right? So regular expression for the white spaces. Simply delimiter followed by one or more number of occurrences of the delimiters. Right? So delimiter followed by one or more occurrences of the delimiters. Then relational operators. Recognizing the relational operators. Now, this is a transition diagram to accept and to check all these relational operators. Right? So, here, less than. If it is followed by equal, less than equal. If it is followed by greater than, it reaches the final state 3, says it is not equal. If it is any other characters, then simply it will return the relation operator less than. Right? It will repeat simply return the relation operator less than. If it is assignment. So simply equal, right? Then greater than symbol followed by assignment. So greater than equal. Other it is greater than symbol is followed by any other symbol. Simply we say it is a relational operator greater than. So this is a transition diagram which recognize the all the relational operators, right? Then recognizing the numbers. Previously we have seen the regular expression, right? So this is the regular expression that we have seen the numbers. Now this is a transition diagram to recognize the regular expression for the number. We start with the initial state. It may accept a single digit and goes to the final state specifying that it is a acceptable number containing the digits, right? Then then so simply 1. If 1 2 says that 1 followed by 2, it may repeat it. If it is followed by any other delimiters, then goes to the here and print it is a number. If it has a optional, means it may reach this one if it only has a digits. If it is a dot, it is having a decimal point, then it will followed by one or more number of digits. A optional says that if it is a decimal point, then it must be have followed by a sequence of digits. Then it is followed by white spaces. Then it goes to this final state and says that it is a number containing digits followed by a fractional part. Only the digits, this is the final state. If it is containing fractional part, then this is the final state, right? Then it may followed by exponent part. If it is followed by explanation part, right? If it is followed by explanation part. So if E to represent exponent, it may follows by sign followed by digit or only digits. If it is followed by any other characters, then goes to the final state, says that it is a number containing digits, fractional part and exponent part. If it is a sign, it will be followed by, if sign is there, it will be followed by a list of digits. Then, if it is the exponent may followed by simply a digits. And it reaches the a final state, right? So if we repeat any number of digits, right? So this is a transition diagram for the numbers, right? So regular expressions are key representations of to token. To recognize the regular expressions, convert the regular expressions to NFA and simulate the NFA. Convert the regular expressions to an NFA and convert the NFA to DFA and simulate the DFA. So here transition diagram. So what is a transition diagram? Transition diagram is a finite atom. The finite atom might be DFA, NFA, NFA with epsilon. So here that we have to convert these regular expressions to NFA with epsilon, if need to NFA, then to DFA, right? So what is a finite state machine? Here a machine is a mechanical power and having several parts which with a definition function and together performing a task are things we do mechanistically. Okay, so here finite state machine, a finite state automata, right? So here things we do mechanistically, right? Now we'll discuss what is a finite automata. Here it has a finite control which consists the some number of states. It will read the input from the input tape. It will read the input from the input tape and it will move from one state to another state and it will reaches to a final state if it is accepted. Otherwise, it is not accepted. Right? Here, finite automata is device shown above consisting the tape and control circuit which satisfy the following conditions. The tape has the left end and extends to the right without an infinite tape. It means an infinite tape. It will read the characters one by one. The tape is divided into squares in each of which a symbol can be written prior to the start of the operation of the automata. The tape has a read-only head. Head is always leftmost square at the beginning of the operation. The head moves to the right one square every time it reads the symbol and it never moves to the left. When it sees no symbol, it stops and the automata terminates its operation. There is a finite control which determines the state of the automata and controls the movement of the head. So, the input tape is input data, input characters of the data is written on the tape. The tape reader always initially represent the left hand symbol and it will read the input symbol one by one. After reading each symbol, the finite control moves from one state to another state. If the input symbols are read, if it is followed by empty symbol, simply it says the end of the input. Then the finite automata stops the operation and it will conclude if it is reached the final state, the input is accepted. And if it is not reached the final state, then we say it is not accepted. So this is the complete picture of the finite automata, right? The finite automata. Here, finite automata with gives output and finite automata without output, right? Here, for every input symbols, there will be output symbols. Then, these are the Moore machines and Mealy machines. There are 5 input symbols, so there will be output also. There are 4 or 5 output symbols. This finite automata which gives the output string, then we'll say as Moore machines and Mealy machines. Here, a finite automata it simply says the string is accepted or not. Say yes or no without output. Then we say there are deterministic finite automata, non-deterministic finite automata, and NFA with epsilon symbols. Epsilon means empty symbol. So NFA with empty symbols, NFA with epsilon. So these are the different forms of the finite automata. The first one is deterministic finite automata. Here we represent the finite automata First one is deterministic finite automata, DFA. The first point, what is a DFA? DFA says that it will read the input characters. For each input character, there is some output state. For each input symbol, there will be some output state. So, it will have a one and only one transition for every input symbol. Right? It will have one and only one output transition for every input symbol. Right? So, a deterministic finite automata will represent with a 5-tuple notation. So, there will be 5 symbols. Right? There will be 5 symbols. A 5-tuple notation. Right? The first one is a set of states. Q says a set of states. Right? Q will represent a set of states in that DFA. Then, this one sigma is input alpha bit. All the accepted input alpha bits are represented with this. Symbols are represented in this alphabet. This is input alphabet. Is an input alphabet which consists all acceptable symbols for the finite automata. Then it is a transition function. Data is a transition function. We represent this transition function in the form of state and input symbol will give a state. Right? A state on input alphabet will give a state, which means that for every input symbol there is one and only one output state. So every input symbol there is only one transition and it will give one output state. Right? A state and input alphabet gives a state. Right? Then initial state. Then comes to the initial state. The initial state says that the starting state of the finite automata, where we start reading the input characters. Then it will move from one state to another state. Right? So the initial state, which belongs to set of states, and we represent the initial state as the Q naught. Right? We represent with the Q naught. Then the final symbol is a set of final states. A set of final states. It consists it specifies all the accepted final states. If any input symbols results to this final state, then the string is accepted. If we not reach the final state, then simply we says the input string is not accepted. So a set of final state will be a subset of or equal to our set of states. Q consists all the states of the finite automata. F consists all the final states which may the subset are equivalent to the states of the finite automata. Right? Here, all the final states are denoted by a double circle. Right? All the final state, accepting states will be denoted by double circles. Right? So here, we are saying the transition function. A state on input alphabet gives a state. So, we represent this Cartesian product of state and input alphabet simply as 2 tuples notation, state followed by a input alphabet. A state and input alphabet. So, Q belongs to a set of state, A belongs to input alphabet. Will results to a one and only one transition and only one output state, right? So accepting the all the input characters, it will move from one state to another. So on which input there is one and only one state to which automata can transition from its current state, otherwise it is called the non-deterministic finite automata, right? We are saying DFA, NFA. If there is only one output transition for the state and input symbol, then it is say as deterministic finite automata. One and only one state to which automata can transition from its current state. If not, then we say NFA, non-deterministic finite automata. Then we say a non-deterministic finite automata, right? So here we always start with the initial state Q naught, and it will read a word, a W, which is a sequence of characters, and finally it reaches the H state. If it is a final state, then it is accepted. If it is unable to reach the final state, then it is rejected. Right? Here, after reading the input characters, after reading the input characters, it will move from initial state to another state. For each input character, it will change one state to another state. It will have one transition. Might be it will be the same state also, right? A state on accepting input symbol may reach the same state, but it will have some transition. And after reading all the input characters of the word W, then it will be reaches to some final state, then the string is accepted. Otherwise, the string is not accepted. Right? So, today we end this class by discussing the definition of this DFA. So, in the next class, we'll discuss some examples of the DFA and we'll continue with the topics of NFA with epsilon. Right? So, today I'm closing this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.